Welcome! Today, we'll explore problem number 643, maximum average subarray I. This problem challenges us to compute the maximum average of contiguous subarrays of a given length. We'll break down the solution step by step, starting with a brute force approach and analyzing its complexity. Let's dive in. The problem asks us to find the maximum average value of any contiguous subarray of a given length k within an integer array nums. Essentially, we need to identify a sequence of k consecutive elements in the array that, when averaged, produces the highest possible value. This average should be returned as a floating point number, and answers within a precision of 10 to the power of -5 are considered acceptable. For the input format, we are given the array nums, where each element lies between -10,000 and +10,000, and the length k, which must satisfy the condition that it is at least 1 and no greater than the length of the array. The output is a single floating point value that represents the maximum average we can compute. To better understand, let's look at some examples. In the first example, we are given the array 1, 12, -5, -6, 50, 3, and k equals 4. The goal is to find a subarray of length 4 with the highest average value. The subarray 12, -5, -6, 50 gives us the sum of 51, which translates to an average of 12.75 when divided by 4. Hence, the output is 12.75. In the second example, the input array is 5 and k equals 1. Since there is only one element, the subarray must be 5, and its average is simply the value of the element itself, which is 5.0. These examples illustrate how the problem works for different array lengths and subarray sizes. Now, in the third example, we are given the input array 0, 4, 0, 3, 2, and k equals 1. When the subarray length is 1, we are essentially looking for the largest single element in the array. Among the elements, 4 is the largest, so the maximum average is 4.0. Moving on to the constraints, the array length n can be as large as 100,000, and k can range from 1 to n. Each element in the array can range from -10,000 to +10,000. Given these constraints, the solution must handle both large inputs and a wide range of values efficiently. Additionally, the problem specifies that answers within a precision of 10⁻⁵ are acceptable. Let's also consider some important edge cases. For the smallest possible input, where nums contains just one element and k equals 1, the maximum average is simply the value of that element. For example, if nums equals 1 and k equals 1, the result is 1.0. In cases where the array contains large values, such as 10,000, -10,000, 10,000, -10,000, with k equal to 2, the solution must handle these extreme values without overflow or errors. For arrays with all negative numbers, like -1, -2, -3, -4, and k equals 2, the maximum average would still be the least negative average. Lastly, when both n and k are very large, such as when n equals 100,000 and k equals n, the solution needs to be efficient enough to process the entire array and compute the average of all its elements. These edge cases emphasize the importance of both correctness and performance in the solution. To solve this problem, we first consider two possible approaches. The brute force approach is straightforward and relies on calculating the average of every contiguous subarray of length k. The idea is simple: iterate through all possible starting indices, compute the sum of the subarray for each starting point, and then calculate the average. While this works, it has a significant drawback. The time complexity is n*k, because for each of the nk+1 starting indices, we explicitly compute the sum of k elements. This can become computationally expensive as the size of the array or the value of k increases. On the other hand, we have the sliding window approach, which is a much more efficient optimization. Instead of recalculating the sum from scratch for each subarray, we maintain the sum of the current window and update it as the window slides. This means subtracting the element that leaves the window and adding the element that enters it. This reduces the time complexity to n, as each element in the array is processed only once. Additionally, the space complexity remains 1, as no extra data structures are needed. By avoiding redundant calculations, the sliding window approach is faster and more suitable for large inputs, making it the preferred solution for this problem. The sliding window approach stands out as the optimal strategy for solving this problem. The key insight here is that finding the maximum average subarray of length k is equivalent to finding the maximum sum subarray of the same length, since the divisor k is constant across all averages. This allows us to focus solely on maximizing the sum. By leveraging the sliding window technique, we reuse the sum from the previous subarray and update it incrementally as the window shifts. This eliminates the need to recompute sums from scratch, which was the main inefficiency in the brute force approach. The big realization here is that by making these incremental updates, we reduce the time complexity to O(n), which ensures the solution is efficient even for large arrays. Compared to the brute force method, this approach is not only faster but also simpler to implement. By avoiding nested loops, the code becomes cleaner and easier to follow, which is especially valuable in debugging and maintaining the solution. While the sliding window approach does assume that the input constraints are valid, such as k being within the proper range, this assumption aligns with the problem statement and makes it an ideal choice for this scenario. In summary, the sliding window approach provides the perfect balance between efficiency and simplicity, making it the best choice for this problem. While the brute force method can help build an initial understanding, it quickly becomes impractical for larger inputs due to its high computational cost. The sliding window method addresses these inefficiencies by eliminating redundant calculations, scaling well even with maximum constraints. Its intuitive implementation, combined with its optimized performance, demonstrates why it's the preferred strategy. This balance of practicality and elegance is what makes the sliding window approach not just a solution to this problem, but also an invaluable technique for similar challenges in competitive programming and real-world applications. The goal of this problem is to find the contiguous subarray of length k that has the highest average value. To do this, we need to focus on maximizing the sum of the elements in the subarray, since dividing by k is constant for all subarrays of the same length. A brute force approach would involve checking every possible subarray of length k, calculating their sums, and determining the maximum. However, this approach becomes computationally expensive as the array size increases. Instead, we can use the sliding window technique to optimize the process. The first step is to calculate the sum of the first k elements, which forms our initial window. We store this sum as the maximum sum observed so far. This setup allows us to start optimizing the process as we move through the array incrementally. Now, to slide the window across the array, we iterate from the kth element to the end of the array. For each step, we update the window sum by subtracting the first element of the previous window and adding the current element. This adjustment ensures that we maintain a rolling sum without recalculating everything from scratch. After updating the window sum, we compare it to the current maximum sum. If the new sum is greater, we update the maximum sum. Once we've processed the entire array, we compute the maximum average by dividing the maximum sum by k, and then return this result. The sliding window approach is highly efficient because it avoids redundant computations, focusing only on the minimal changes required to shift the window. By reusing previous calculations, we significantly reduce the time spent analyzing subarrays. The sliding window technique reduces the time complexity of this problem from O(n*k), which is the brute force approach, to O(n), as each element is processed only once. This efficiency comes from avoiding the recomputation of sums for overlapping subarrays. There are also a few edge cases to consider. If k equals the size of the array, the entire array is the only possible subarray, so the result is simply the average of all elements. The algorithm also handles negative numbers correctly because it focuses on maximizing the sum, regardless of the sign. Additionally, it's important to ensure that k is valid, meaning it must fall within the range from 1 to the length of the array. The algorithm uses only a few variables to track sums and indices, making it space efficient. Arrays hold the input data, and the sliding window technique keeps memory usage minimal by avoiding auxiliary data structures. Let's walk through an example to see the algorithm in action. Suppose the input array is 1, 12, -5, -6, 50, 3, and k is 4. First, we calculate the sum of the first four elements, 1 plus 12 to 5, 6, which equals 2. This becomes our initial window sum and our current maximum sum. Next, we slide the window by adding the fifth element, 50, and removing the first element, 1. This gives us a new sum of 2 to 1 plus 50, which is 51. We update the maximum sum to 51. Sliding the window again, we add the sixth element, 3, and remove the second element, 12. This results in a new sum of 51 to 12 plus 3, which is 42. The maximum sum remains 51. Finally, we calculate the maximum average by dividing the maximum sum, 51, by k, which gives us 12.75. This demonstrates how the algorithm efficiently tracks the maximum sum using the sliding window technique. The time complexity of this algorithm is O(n), because we process each element in the array only once while sliding the window. This makes it significantly faster than the brute force approach for large arrays. The space complexity is O(1), since the algorithm only uses a few variables to maintain the current window sum, maximum sum, and indices. No additional data structures are needed beyond the input array. This combination of linear time complexity and constant space usage makes the sliding window approach highly efficient and well-suited for solving this problem. This Python implementation solves the LeetCode problem number 643 maximum average subarray using a sliding window technique. The function findMaxAverage takes two arguments, nums, a list of integers, and k, the size of the subarray. First, the code calculates the sum of the first k elements of the array and initializes two variables, current_sum and max_sum, to this value. This represents the sum of the initial sliding window. Next, the function uses a for loop to slide the window across the array, starting from the kth index up to the end of the array. In each iteration, the sliding window is updated by adding the new element at the current position, nums, I, and removing the element that falls out of the window, nums, I, k. This ensures the window always contains exactly k elements without recalculating the sum from scratch. After updating the current_sum for the current window, the function checks whether this new sum is greater than the previously recorded max_sum. If so, it updates max_sum to the new value. Once the loop completes, the function computes the maximum average by dividing max_sum by k and returns the result. This ensures the solution is optimized to O(n) time complexity, as the array is traversed only once, and the memory usage remains constant at O(1). This implementation is concise, efficient, and handles edge cases like arrays with negative numbers or small values of k seamlessly. This is the Java implementation of LeetCode problem number 643, maximum average subarray. The logic mirrors the Python solution, using a sliding window approach to find the maximum average of any subarray of length k. The sum of the first k elements is initialized, and the window is adjusted by adding the next element and removing the first element of the previous window. Key differences include Java-specific type declarations and the use of math.max for maximum value comparison. In this example, we are tasked with finding the subarray of length k that has the maximum average in the given array nums. Let's start by calculating the sum of the first k elements, which forms our initial window. Adding the first four elements, we get 1 plus 12, 5, 6 equals 2. This sum, 2, becomes our current_sum, and since it's the only sum we've calculated so far, it also becomes our max_sum. At this stage, our current_sum and max_sum are both equal to 2. Now, we will use a sliding window approach, moving the window one step at a time and updating the sums accordingly to determine the maximum sum for any subarray of size k in the array. As we slide the window, we first move to the subarray ending at index 4. Here, we update the current_sum by adding the new element 50 and removing the first element 1 from the previous window. This gives us current_sum equals 2 plus 50, 1 equals 51. Next, we compare this current_sum with our max_sum and update max_sum to the larger of the two values. In this case, max_sum becomes 51. Moving to the next subarray, which ends at index 5, we update the window sum again by adding 3 and removing 12. This results in current_sum equals 51 plus 3, 12 equals 42. We compare this with our max_sum, which remains 51 because it is greater. At the end of this process, the maximum sum over all subarrays of size k is 51. Dividing this max_sum by k gives us the maximum average, which is 51/4 equals 12.75. The result for this example is a maximum average of 12.75. Now, let's consider another case where the array consists entirely of the same value, 5, and k is equal to 3. Here, the sum of the first k elements is straightforward since all the elements are equal. Adding the first three elements gives us current_sum equals 5 plus 5 plus 5 equals 15. This sum is also our max_sum at the start. With this initialization done, we will now slide the window through the array, updating the sums as we go. Sliding the window to the subarray ending at index 3, we add the new element 5 and remove the first element 5. This results in no change to the current_sum, which remains 15. Comparing this with max_sum, we see that max_sum also stays 15 since the values are equal. Moving to the next subarray ending at index 4, we again add 5 and remove 5, leaving the current_sum unchanged at 15. The max_sum remains 15 as well. Since all elements in this array are identical, every subarray of size k produces the same sum. Dividing this max_sum by k gives us the maximum average, which is 15/3 equals 5.0. The result for this example is a maximum average of 5.0. Finally, let's analyze a case where the array contains negative numbers, specifically, -1, -2, -3, -4, -5, and k is equal to 2. Here, we calculate the sum of the first k elements, which gives current_sum equals -1 plus -2 equals -3. This initial sum also becomes our max_sum. With this setup, we begin sliding the window to calculate the sums for subsequent subarrays of size k. For the subarray ending at index 2, we update the current_sum by adding -3 and removing -1. This gives current_sum equals -3 plus -3, -1, equals -5. Comparing this with max_sum, we see that max_sum remains -3 because it is greater than -5. Next, for the subarray ending at index 3, we add -4 and remove -2, resulting in current_sum equals -5 plus -4, -2, equals -7. Again, max_sum stays -3. Finally, for the subarray ending at index 4, we add -5 and remove -3, giving current_sum equals -7 plus -5, -3, equals -9. The max_sum remains -3 as it is still the largest sum. Dividing this max_sum by k, we find the maximum average to be -3/2 equals -1.5. The result for this example is a maximum average of -1.5. To determine the time complexity of our solution, we start by analyzing the sliding window technique. First, during initialization, we calculate the sum of the first k elements of the array. This step involves a single iteration over the first k elements, so its time complexity is O(k). Next, as we slide the window across the array from index k to the end, we update the sum by adding the next element and removing the first element of the current window. This update process takes constant time, O(1), for each iteration. Since there are n k elements remaining after the first window, the sliding operation takes O(n)k) time in total. When we combine both steps, the total time complexity is O(k) plus O(n)k), which simplifies to O(n), as n dominates when the input size is large. Now, let's examine the space complexity. The solution operates using only a constant amount of extra space. Specifically, we use two integer variables, current_sum and max_sum, to store the ongoing sum of the current window and the maximum sum found so far. Since these variables require a fixed amount of space regardless of the size of the input array, their space usage is O(1). Additionally, since the algorithm operates directly on the input array and doesn't allocate any additional data structures, the overall space complexity of the solution is O(1). This makes the approach highly memory efficient. Comparing this optimized sliding window approach to a brute force method highlights the efficiency gains. In a naive solution, we would calculate the sum of every possible subarray of size k. For an array of length n, there are n k plus 1 subarrays, and summing up each of these subarrays involves iterating over k elements. This results in a time complexity of O(n)k), *k, which simplifies to O(n)*k). However, the optimized sliding window approach avoids recomputing the sum for each subarray by reusing the sum of the previous window. This reduces the time complexity to O(n), a significant improvement. Both approaches have the same space complexity of O(1), but the sliding window technique is far more efficient in terms of runtime. Finally, let's analyze the algorithm across best, average, and worst cases. In the best case, even if the array has uniformly distributed values, the algorithm still needs to iterate through the entire array, so the time complexity remains O, n. In the average case, for arrays with random distributions of values, the procedure and complexity remain unchanged. Similarly, in the worst case, where the array contains extreme variations in values, the operations performed by the algorithm do not change. This consistency ensures that the time complexity is always O, n. Mathematically, this is because the sliding window performs a constant amount of work, O1, for each of the n k iterations, giving O, n k. Adding the initialization step, which is O, k, results in O, k, plus O, n k, which simplifies to O, n. With this linear time complexity and constant space complexity, the solution is efficient and scalable. One common mistake when solving this type of problem is neglecting edge cases. For example, what happens when the value of k is larger than the length of the array, or if the array is empty? These scenarios can lead to runtime errors or incorrect outputs, so it's essential to validate the inputs and handle such cases explicitly. Another frequent mistake is relying on a brute force approach to calculate the sum of all subarrays of size k. While this may seem straightforward, it results in a time complexity of O, n squared, which is inefficient for larger arrays. Instead, using the sliding window technique allows you to optimize the summation process to O, n. Additionally, errors can occur if the sliding window is not updated correctly. For instance, forgetting to subtract the element leaving the window or incorrectly adding the new element entering it can lead to inaccurate calculations. Lastly, floating point precision issues can arise when working with averages. To mitigate this, you can perform intermediate calculations using integers and only divide at the end, minimizing the risk of precision loss. Another pitfall is misunderstanding the constraints of the problem. For instance, assuming all numbers in the array are positive might lead to incorrect results when negative numbers are present. Always take the time to fully understand the constraints before implementing your solution. From an interview perspective, recognizing patterns like sliding window is critical, as it's a common optimization technique for problems involving contiguous subarrays. Mastering this pattern not only helps reduce time complexity significantly but also demonstrates your problem-solving skills. Interviewers often focus on edge cases, such as arrays with all negative numbers, k equal to 1, or k being the length of the array. Preparing for these scenarios shows thoroughness. Additionally, it's important to articulate the trade-offs of your approach. For example, explaining why the sliding window method outperforms brute force in terms of time complexity and space efficiency can make a strong impression. Finally, be ready to think about scalability and precision, particularly in follow-up questions about handling extremely large arrays or avoiding floating point calculations altogether. When it comes to related problems, many follow a similar sliding window approach. For instance, LeetCode 209, minimum size subarray sum, involves finding the smallest subarray with a sum greater than or equal to a target value. LeetCode 643, the current problem, is slightly simpler as it focuses solely on finding the maximum average. LeetCode 424, longest repeating character replacement, applies the sliding window technique in a different context, dealing with character replacements. Similarly, LeetCode 1004, max consecutive ones 3, uses a sliding window strategy to maximize the number of ones in a binary array after flipping at most k zeros. Beyond these examples, it's also helpful to consider alternative approaches. The brute force method, while conceptually easy to grasp, involves computing the sum of every subarray of size k, resulting in a time complexity of O, n squared. While it's simple to implement, it's impractical for large arrays. In contrast, the sliding window approach maintains a running sum for the current window of size k, updating it as the window slides. This method is far more efficient, with O, n, time complexity and O, 1, space complexity, though it does require careful implementation to avoid mistakes. Another alternative to consider is the prefix sum approach. By pre-computing the prefix sums of the array, you can calculate the sum of any subarray in constant time, O, 1. This reduces the time complexity of the overall solution to O, n. However, there is a trade-off. The prefix sum method requires additional space to store the prefix array, making it less space efficient compared to the sliding window approach. While this might not be an issue for smaller arrays, it's something to consider when working with memory constraints or extremely large datasets. Each of these approaches has its strengths and weaknesses, so understanding their trade-offs allows you to choose the most appropriate solution for a given problem or scenario. Thank you for following along. In this session, we tackled problem number 643 and reviewed a brute force approach to find the maximum average subarray. Remember to practice optimizing solutions and experimenting with edge cases. If you enjoyed this walkthrough, please like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!